So hello everyone again. This is lecture 3 part 3 of ray optics and optical instruments. In the previous lecture we successfully derived the lens maker's formula and the lens equation. Today we will move on with the further discussions of this refraction by lenses only, and then we can move on further with the refraction through a prism. So I am Samir Levankar. Let's begin our discussion. So right now we are on the fifth point, that is the reflection at a spherical surface and by lenses. So in the last lecture we derived it for the convex lens, double convex lens to be very precise. So first we moved on the lens maker's formula. So what is the lens maker's formula? It is equal to 1 by f, which is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2. And similarly, what is the lens equation? Lens equation is nothing but 1 by v minus 1 by u is equal to 1 by f. Okay, let's move on with the further discussions today. So to find the image of an object via lens, we can in principle take any two rays emanating from a point on an object, trace their path using the laws of refraction, and find the points where the refracted rays meet or appear to meet. So what does it try to say is, as in the same concept of reflection, what we did is we basically derived or basically found out 2, 3 or 4 such rays for which the basic principle concept we already know, such that if there is a passing ray which is coming from the infinite position, if the object is at infinite, then after reflection it will go on with the through the focus. Similarly, if it is going through the pole, then it will go at the same angle. So we know the same angle there also. Then if the angle of incidence is happening through the focus of the mirror, then it will go parallel to the principal axis. So these were the 3-4 points which we know for reflection. Similarly, we know the basic principles for refraction also. So if we need to find out the basic agenda or basic points where the image will be found, we can derive it similarly using these 3 or 4 lines which are written after this line. So let's move on. Let us understand these 3-4 lines also. So in practice, however, it is convenient to choose any two of the following rays. So what are the rays being talked about here? So first of all, a ray emanating from the object parallel to the principal axis, and ray emanating from the object parallel to the principal axis. So let us suppose this is that image, sorry, it is that ray of the lens after refraction passes through the second principal focus f dash in a convex lens, or appears to diverge from the principal focus f. So what does it try to say is basically it passes through this focus f dash. So this is being talked about in the first lecture for the convex lens, and similarly for the concave lens, what is happening is it tries to appear in this form, so that it is diverging from the first focus. This is the first line. Next line is, a ray of light passing through the optical center of the lens emerges without any deviation after refraction. So it is saying that if it is passing through the optical center, then there is no deviation, it will go in the straight portion only. So this thing is also been explained. So this is valid for this portion also here. Okay, next thing is that third is divided into two parts here. So first is a ray of light passing through the first principal focus of a convex lens. So let us suppose we are passing the ray of light through the first principal focus, emerges parallel to the principal axis after refraction. So basically it is parallel to the principal axis. This is being talked about. This is the third ray. Okay, a ray of light incident on a concave lens appearing to meet the principal axis at the second focus emerges to the principal axis after refraction. So what is it trying to say is, if we are trying to assume, or if we are trying to say that, let us suppose there is no refraction happening, and this will virtually intersect the second focal length, second focus point, then focal point, then the ray of light after refraction is parallel to the principal axis. This is your third point. This is your third ray. So these are the 3 rays only. So any of the 2 rays can be chosen, and then if the intersection point is being formed, then we can find out the value of image. So this will you can find out the value of height. Okay, let's move on. So this is the basic what we can say analogy of reflection being used in the refraction concept here. Okay, let's move on. So next is the figure illustrate these rules for a convex and a concave lens respectively. Here again it must be remembered that each point on an object gives out infinite number of rays, quite evident. So basically the rays would be emanating in this sequence also. but for these sequences we just do not know the actual ray of which is happening, therefore we take these 3 sequences only, but actually so they will refract in this form only, all will reach this image A only. Okay, let us move on. So, here again it must be remembered that each point on an object gives out infinite number of rays. All these rays will pass through the same image point after refraction at the lens, quite evident, it will pass through the same point only. Okay. Magnification M produced by a lens is defined like that for a mirror as the ratio of the size of the image to that of the object. Quite evident, we know what is magnification. Magnification is nothing but h dash upon h. So, proceeding in the same way as for spherical surfaces, it is easily seen that for a lens M is equal to h dash upon h, which is equal to V by U. So, when we apply the sign convention, we say that for erect and virtual image formed by a convex or concave lens, M is positive, quite evident, while for an inverted and real image, M is negative, quite evident. So, here the image formed is your inverted image, and sometimes it will be formed as a erect image. Okay. Let us move on to a simple example now. So, a magician during a show makes a glass lens with n is equal to 1.47 disappear in a trough of liquid. What is the refractive index of the liquid? Could the liquid be water? So, the refractive index of the liquid must be equal to 1.47 only in order to make the lens disappear. This means n1 is equal to n2, and that then only the glass lens will make it disappear. Why it will be n1 equal to n2? Because then only what will happen is n2 by n1 will be equal to 1, and hence 1 minus 1, which is equal to 0 will happen, and hence we can say that f is either infinite using the lens makers formula. Okay, so this gives you n by f is equal to 0 or f is equal to infinity. Hence the lens in the equation will act like a plain sheet of glass. No, the liquid is not water. So, for the second equation we can say, second answer we can say that the liquid is not water, it could be glycerin only. Why? Because the refractive index of water is 1, as the refractive index is greater than 1, hence it is not water. It can be either anything which can be a little thick, optical density little higher. So, for clear assumption we can say it is equal to what we can say glycerin. Okay, let us move on. So, next is power of a lens. So, basic concept again which you have heard, which you have understood in the class 10th also. Let us move on with the discussion. I think a little detail is being talked about here. So, let me try to understand, explain you bit by bit. Okay. So, first of all, what is power of a lens? Power of a lens is basically a measure of the convergence or divergence which a lens introduces in the light falling on it. So, what does it try to say? It just tries to say what is the power through which it can diverge or converge. So, basically a convex lens will try to converge it, concave lens will try to diverge it. So, what is that measure of power? What is the capacity to converge or diverge it is basically the power of a lens. So, the power of a lens is a measure of the convergence or divergence which a lens introduces in the light falling on it, quite evident. So, how is this name derived? I will try to explain to you. So, first let me iterate everything which is written here. So, clearly a lens of shorter focal length bends the incident light more, while converging it in case of a convex lens and diverging it in the case of concave lens. What does it try to say is, let us suppose we take two instances. The first instance is that it is having the focus here and this is having a focus here. Let me note it as f1, this is f2, f2 is greater than f1. So, as you can see, any light which is passing through it converges in this form, any light which is passing through it converges in this form. As you can see the power of this lens to converge it is very high than this. Let me take another sequence here. Let us say I take f2 here. If I take f2 here, as you can see that the amount to converge is much higher than this sequence is also. So, what we can say that if the focal length of a lens is small, then the amount or the convergence power of that lens increases, and this is the only concept or this is the only agenda of power of a lens. Okay, let us move on. So, clearly a lens of shorter focal length bends the incident light more, while converging it in the case of convex lens and diverging it in the case of concave lens. The power P of a lens is defined as the tangent of the angle. Please look over here carefully. The power P of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light parallel to the principal axis, falling at the unit distance from the optical center. So, basically this is the mathematical formulation being explained here. Therefore, this is tan delta. So, tan delta is nothing but equal to H upon F. What is H here? H is this. What is F here? F is this. Okay. So, now if H is 1, so what if H is equal to 1, then tan delta is equal to 1 by F, because we are assuming it for unit distance from the optical center. Therefore, what we can assume is that this is nothing but equal to power. Hence, we define the equation for power. Power is nothing but 1 by F, or the reciprocal of the focal length is nothing but the power of a lens. Okay. Please very much remember, because the complete assumption is based on tan delta is approximately equal to sin delta is approximately equal to delta. So, we can assume tan delta is equal to delta, hence approximately equal to delta, hence we can write delta is equal to 1 by F. Okay. Thus, P is equal to 1 by F. The SI unit of power of a lens is diopter. So, you may have heard this in your 10th class also, just again reiterating stuff. So, SI unit of power is nothing but diopter. The power of a lens of focal length of 1 meter is 1 diopter. Quite evident. If you will put the value of F is equal to 1, then you will get the power is equal to 1 diopter. Power of a lens is positive for a converging lens. Why? Because the radius is positive and therefore focal length is positive, and negative for a diverging lens. Why negative? Because the focal length is negative as the radius is negative. What is radius? Radius is nothing but radius of curvature. Okay, so this thing is also been explained, this thing is also been explained. Now, thus when an optician prescribes a corrective lens of power plus 2.5 diopter, the required lens is a convex lens, quite evident, of focal length plus 40 centimeters, because 1 by 2.5 is nothing but. Similarly, so this is nothing but equal to 40 centimeters. Okay. Next thing is your a lens of power of minus 4 diopters means a concave lens of focal length minus 25 centimeters. So, basically it is 1 by minus 4, which will give you minus 25 centimeters. So, basically as this gives you the value in meters. So, basically actual answer which it will give you is your 0.4 meters. I convert it into 40 centimeter. Similarly, for this it is being converted from 0.25 meters to 25 centimeters. Okay. So, this is the discussion of a power of a lens. Let us move on to typical examples for your lens maker's formula, lens equation and power of a lens now. Okay. So, please look over here carefully. First of all, let us look at the first question now. So, given there that if if focal length is equal to plus 0.5 meter for a glass lens, what is the power of the lens? It's very easy. You know, power of a lens is equal to 1 by F, which is equal to 1 by 0.5, which is equal to 1 by 2, which is equal to 2 diopters. So, power is equal to 2 diopters here. Let us move on to the second question now. The radii of curvature of the faces of a double convex lens are plus 10 and plus 15 centimeters. 10 and 15 centimeters. Please remember, for one it will be positive and for one it will be negative. Its focal length is 12 centimeters. What is the refractive index of the glass? Quite evident. So, we can just directly use the value of n to 1. So, first of all, what is the equation being used here? Equation used is 1 by F is equal to n to 1 minus 1 into 1 by R1 minus 1 by R2. So, what will happen here? Basically, what you need to find out, focal length is given. So, focal length will be nothing but plus value only, because convex lens is being used. N to 1 is to be calculated 1 by R1. Please remember here now, please sign conventions are to be used. For the first it will be positive. Why? Because it is in this direction. For second it will be negative. Why? Because it is in the measurement of the radius is in the opposite direction of the direction of incidence of light. So, this will be minus 15. Okay. So, nothing but n to 1 minus 1 into 1 by 10 plus 1 by 15, which will be equal to n to 1 minus 1 into 15 plus 10 upon 150. Therefore, n to 1 is equal to 1 plus 12, sorry, 150 upon 12 into 25, if I am not wrong. Okay. Hence, you will get the value of answer equal to 1.5 here. So, 150 by 25. Yes, okay. So, this is correct. So, you will get the answer equal to n equal to 1.5. Okay, let us move on to the third question now. The third question says that a convex lens has plus 20 centimeter focal length in air. That means the focal length is 20 focal length in air, and so f is given to you as plus 20 centimeters. What is the focal length in water? So, basically in air it is given, that means the value at n1 is n as equal to 1 is given to you, right. The refractive index of air water is given to you as 1.33 and refractive index of air glass is given to you as 1.5. Okay, so basically a question is being asked here in which there was first of all a I understood the question. So basically it's again a lens makers equation only. For the first instance we are assuming a air glass interface, and for the second instance we are assuming a air water interface. Okay, so again simple mathematical formulation only. So basically we know 1 by f is equal to nothing but n to 1 minus 1 into 1 by r1 minus 1 by r2. So using the equation twice, as the value of radius will be same, so we can just derive this equation equal to n for glass minus 1 into focal length is equal to n for water minus 1 into focal length. Now for glass you have the value of 1.5, focal length in air is given to you, this NW is given to you as 1.33, this focal length has to be calculated. So after calculation you will get the answer equal to 78.2 centimeters. Okay, so this is that example being explained here. Okay, so for this discussion let me stop the discussion here only, because that will be a little tedious if I explain you everything in the same lecture only. So let me stop it here only. In this lecture what we understood is basically after the conclusion of this lecture, first of all you know the mirror equation, that is 1 by v plus 1 by u is equal to 1 by f. The second was your lens maker formula, that is 1 by f is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2, and the third equation is for thin lens formula, it is 1 by v minus 1 by u is equal to 1 by r, sorry 1 by f. Okay, so these three are the similar equation which you know. The next concept was the power of a lens. So power of a lens is nothing but the measure of the convergence of a lens. It is applicable for both convex lens also, concave lens also, it just depends upon the sign convention. Power of a lens is nothing but 1 by f, which is diopter. And finally we derive I explained you a simple example of sign conventions and mirror equation. So for this lecture let me stop it here only. In the next lecture I will start with the example of a combination of thin lenses. So what will happen if I try to combine the lenses like this, and then we will move on to the prism concept. So let me stop it here. Thank you so much.